Let's turn now to fission, which is what happens when large atoms split up. They may do so spontaneously, or we may have to make them split up, in which case we call that induced fission. Nuclear fission is a process which provides energy for nuclear power stations and indeed for bombs. But why do we get a release of energy? Well, in order for protons and neutrons, which as I've said we call nucleons, to be held together in the nucleus, they have to be bound. We can plot the binding energy per nucleon for each element from hydrogen to uranium. Here I have a chart which along this axis shows the total number of nucleons, that's protons and neutrons, in the nucleus. This shows the binding energy, which is expressed in negative terms, because what it means is that if a proton or neutron is bound in the nucleus, you have to put energy in to get that nucleon out. Now the binding energy per nucleon is shown in a graph that looks something like this. For hydrogen, which sits here, the binding energy is about 1 MeV. For uranium, which sits about here, the binding energy per nucleon, and there are nearly 250 of them, is 7.4 MeV per nucleon. In other words, you would have to put in 7.4 MeV of energy just to get one nucleon out of a uranium atom. The most stable element is iron, and that has a binding energy of about 9 MeV per nucleon. What is the meaning of this graph? What it means is that as you build up elements by combining small elements, you will get energy out. That is a process called fusion. The reason that you get energy out is because the binding energy per nucleon is lower in the more massive elements. But similarly, if you start with large elements and break them down into smaller elements, you also get energy out, because as you go towards smaller elements, the binding energy per nucleon is lower. And the process stops at iron in each direction. What this means is that as a larger atom breaks up and becomes smaller atoms, the mass of the two smaller atoms together is less than the mass of the larger atom. And the difference in mass is converted into energy according to the famous formula E equals mc squared. Similarly, when two lighter elements fuse together to produce a bigger element at this end of the chart, the mass of the bigger element is smaller than the mass of the two smaller elements. And again, there's a mass loss, and that is converted into energy using the E equals mc squared term. Let's consider a typical nuclear fission reaction. If you fire a slow-moving neutron, which is often called a thermal neutron, at a target of uranium-235, which means there are 235 nucleons in the nucleus, there are bound to be 92 protons, because 92 protons means that the element is uranium, and there are therefore 143 neutrons. What you will find is that that becomes, or is split into, krypton with 92 nucleons and barium with 141 nucleons, plus 3 more neutrons. And those 3 neutrons can go round and hit another atom of uranium and split that into these constituent parts. Of course, that can become a chain reaction. And if you're not careful, it can become very dangerous indeed. That's the basis of a nuclear bomb. In a nuclear reactor, those reactions are controlled so that they produce the energy that is required. You'll notice that the total number of nucleons are conserved. We started with 1 neutron plus the 235 nucleons in the uranium atom. And we ended up with 92 nucleons plus 141 nucleons plus 3 extra neutrons. And if you add those together, you get 236, which is the sum of these two. But the uranium binding energy per nucleon is about 7.4 MeV, whereas krypton and barium each have a binding energy of about 8.5 MeV. So there's an energy difference per nucleon of about 1.1 MeV. And since uranium has 235 nucleons, when uranium breaks up, it suffers a mass loss of 1.1 times 235, which is about 260 MeV. 260 MeV worth of energy is released per atom, and that can quickly build up given that there are millions of atoms. That produces energy which in a nuclear reactor is largely in the form of heat, and that's used to drive turbines to generate electricity. But this is not the only way that uranium can split up. Large nuclei of 92 protons and above can split into a whole range of different elements. For example, uranium-235 can split into elements with nucleon numbers from about 80 to 160. The probability of doing so looks like this. In other words, uranium is most likely to split into elements that have 80 or 160 nucleons, but they can split into any element in this range. Fission products can themselves be highly radioactive. The reason is that as a large atom decays, it produces smaller atoms which have proportionately more neutrons than the lighter nuclei would normally have. So if they have an excess of neutrons, they are likely to decay by beta emission, and that is radioactive decay. When atoms decay, they do so according to what is called a half-life. A half-life is simply the time it takes to get half of the starting amount of material that you had. Plutonium is a waste product of nuclear power stations. It's highly radioactive with a half-life of 24,000 years. So that means that if you started off with a ton of plutonium, after 24,000 years you'd still have half a ton. And after a further 24,000 years you'd still have a quarter of a ton. So those radioactive elements can last a long time, and their disposal needs to be carefully controlled. On the other hand, there are radioactive elements that have very short half-lives.